You know, the sun is just blasting our planet with more than enough energy to power, well, everything. But the solar panels we see on rooftops and in fields, they're only grabbing a tiny fraction of it. So, why are we wasting so much of that free energy? And what if we could build a solar cell that was smart enough to catch pretty much the entire rainbow of sunlight? Okay, let's dive into this.
Here's what we're going to cover. We'll start with the silicon ceiling, the thing holding back today's solar tech. Then we'll look at the really clever spectrum sandwich solution. After that, we'll weigh its incredible record-breaking efficiency against its pretty high price tag. And finally, we'll see where this tech is being used right now, which is usually far, far away from your typical rooftop.
All right, first things first. To really get why multi-junction cells are such a big deal, we have to understand the core problem, the fundamental limitation of the solar panels we all know and see every day.
I mean, it's a fair question, right? We see them everywhere, but even the best ones you can buy struggle to turn much more than 20% of the sunlight that hits them into actual electricity. So what is holding them back from getting at the other 80%?
Well, the basic problem is something called the band gap, but you can just think of it as the Goldilocks problem. For a little particle of light, a photon, to make electricity, its energy has to be just right. If a photon has too little energy, like one from infrared light, it just passes right through the silicon. Poof, no electricity. But if it has too much energy, like a photon from blue light, the cell only uses a tiny bit of that energy. And the rest? It's just wasted instantly as heat.
So when you factor in this Goldilocks problem, you run smack into a hard theoretical limit for any solar cell made from a single material like silicon. It's called the Shockley-Queisser limit, and it tops out at around 33%. With our best lab cells already hitting 27%, we are seriously pushing up against a fundamental ceiling set by the laws of physics.
So if a single material has basically hit its limit, how do you get past that ceiling? Well, the answer is an incredibly clever solution that works kind of like a sandwich, but for the solar spectrum.
And this is it, the multi-junction solar cell. Instead of asking one material to do all the work, an MJ cell is a stack of different, specialized layers. Each layer is made of a different semiconductor material, and each one is engineered to have its own unique band gap, perfectly tuned to capture a different slice of the light spectrum.
The absolute best way to picture this is as an energy sieve. Sunlight, full of all these different energy photons, hits the top. That first layer is designed to only catch the highest energy blue and violet light. Everything else passes right through to the middle layer, which is tuned to capture the medium energy green and yellow light. And finally, what's left over, the low energy red and infrared light, gets caught by the bottom layer. It's a team of specialists, and because of that, way less energy gets wasted.
Okay, so let's peek under the hood at a typical setup for one of these high-performance cells. The top layer, made from something like indium gallium phosphide, is built to grab that high-energy visible light. The middle layer, using gallium arsenide, is tuned for the near-infrared part of the spectrum. And the bottom layer, usually made of germanium, is great for catching whatever is left, the low-energy infrared. Each layer is grown with incredible precision right on top of the last one, making a single ultra-efficient device.
Now, a structure this complex, it promises some mind-blowing performance. But, like with any advanced technology, it's all about trade-offs. So let's look at what this means in the real world.
And the results are, well, they're just stunning. While the absolute best silicon cells in a lab are capped around 27%, these multi-junction cells have hit efficiencies of over 46% when you concentrate sunlight on them. That's not just a small step up. In the world of solar, that's like jumping from a propeller plane straight to a jet engine. It's a whole different league.
But it all comes down to a very clear trade-off. On one hand, you get efficiency that nothing else can touch and a really high power-to-weight ratio. On the other hand, the disadvantages are just as big. The exotic materials and the incredibly complex fabrication process, which is honestly more like building a high-end computer chip than a solar panel, make them wildly expensive.
So this high-cost, high-performance profile means that for now, multi-junction cells have very specific jobs. You're not going to find these on your neighbor's roof. So let's see where they actually make sense.
Their use is really focused on two main areas, where performance is absolutely everything, and cost is a secondary concern. The first one is aerospace. For satellites and space probes, every single gram of weight matters and space is limited, so their amazing power-to-weight ratio is a total game changer. The second is something called concentrator photovoltaics, or CPV. These systems use big lenses, kind of like a magnifying glass, to focus a huge amount of sunlight onto one tiny, super-efficient multi-junction cell. That makes the high cost of that one little cell totally worth it.
And this quote from the source material really puts it perfectly. The technology isn't held back by its capabilities, but by its economics. It's a premium top-shelf solution for those jobs where you simply cannot afford to compromise on efficiency or weight.
Which really leaves us with this one big, provocative final thought. We have a technology here that can absolutely shatter efficiency records. It's already powering our missions to other planets. The science is solid, it works. So the ultimate question isn't about physics anymore. It's about engineering and economics. The challenge is clear. Can we find that manufacturing breakthrough that finally brings this incredible space-age tech down to Earth for all of us?